Continuing our study of related rates, we're going to look at a problem which involves a water tank this time. We have a conical water tank with a top radius of 2 meters and a height of 4 meters. So radius at the top is 2 meters and the height overall is 4 meters. Now it's not always full, so we have some water level in here and we have the volume decreasing at 0.5 liters per second. The question we're asked is how fast, so another rate, is the height of the water in the tank changing when the remaining water in the tank is at 2 meters. So again, imagining different scenarios as this is going on, we'll draw this just in cross-section with a few scenarios. What we're going to have is the water level in the tank being high, getting lower, and there's going to be some moment when it reaches 2 meters in depth, or height, whichever way you want to phrase it, and we're interested in how quickly that level is dropping, how quickly that height is dropping at that instant. But notice the height is different at different times, so that's actually a variable as time changes. So let's give that a name. Let's call the height in general h, and let's call the volume v. Both of these are functions of time. And what do we have? We know the rate of change of the volume. There's a hint here that we've got liters per second, so that's volume per unit time. And we know the volume of water in the tank is decreasing. And what do we want? We want dH dt. Perfect. Those are the two rates that we want to relate using our approach. So our first step then is to find the relationship between the quantities, not the rates, but the quantities, in this case here, V and H. Well, H is the height of the water. The volume, I think, is the more interesting part. And if we have the volume of a cone, the volume of a cone is 1/3 pi r squared H. That's an excellent start. The key thing to not get trapped in is don't get tempted to use the 2 meters of the radius, because that was in the problem. That's great, but it's the radius at the top of the tank. The radius when the water is down a bit further is going to be some other amount r. And here we need to do a bit of solving or a bit of work to figure out how that radius changes. Obviously it's getting smaller and smaller as the water level drops. We have less and less water, and so we have a narrower and narrower part of the cone. How do we go about working with that? Well, this is where experience comes in, but this is early geometry. We actually have two triangles in each of these diagrams. One defining the top part, or the absolute outer cone, and inside that we have the water cone, which we can draw off to the side, and we're interested in that cone in h. Well, we already defined that as our interesting variable, and we also have r for that cone. Well, the nice thing about these two triangles is that they're similar, because this triangle of the water fits inside the triangle of that defines the tank. Because the triangle here representing water fits inside the triangle that represents the tank, and so the cones represent the same things, then what we can do is build a ratio. We can build a ratio that the radius to the height is always going to be in a ratio of 2 to 4, or r is going to equal 1/2 the height. Perfect. When the tank is full, 4 meters, we get a radius of 2 meters. As h gets smaller, the radius also is going to get smaller. Let's call that equation 1 and plug that into here. We're going to have volume is equal to 1/3 pi r squared, so 1/2 h all squared times h, and we can tidy that up a little bit. We'll have h squared times h is h cubed, and we'll have 1/2 squared, which is a quarter, times a third is 1/12. Perfect. So now the volume of water that we have in the tank is always going to be given by this function here. This is a relationship that is always true, and it's a relationship between the quantities, V and H. Remember what we want though, we want the relationship between their rates, so this will be our starting point to introduce the calculus. So here's our relationship again. We do exactly the same thing we've done with our earlier implicit derivatives and earlier related rates problems. We take the derivative with respect to time of both sides. That gives us dv dt on the left-hand side, and pi over 12. What's the derivative of h cubed? It'll be 3h squared. And then the derivative of the inside is dh dt. The left-hand side didn't have that much happening because the derivative of any variable with respect to t is just the derivative by itself, or if you like, it's like v to the 1. And now, here we have our related rates. Perfect. And what we wanted was the dh dt. All right, so we want dh dt, so we just solve for that. dh dt is going to equal the dv dt part, and then we're going to divide through by all of this with a little bit of tidying. The 3 and the 12 is going to turn into a quarter. When we bring it to the other side, it'll be times 4 over pi and 1 over h squared. Perfect. It's now a question of subbing in the values. We want this at the time or the instant when h is equal to 2 meters. So notice we don't use that 2 meters earlier on because we want to find the general relationship of the variables. It's just a subbing in at the very end. Be careful not to do that subbing in too early. You need to be able to take the derivatives first, and if you said h was 2 all the time, then h wouldn't change and we wouldn't have a variable for the derivative there, or a value for the derivative. So we want this at h equals 2, and we know dv dt is negative 0.5 liters per second. Now, there is one last ingredient in this problem we do have to deal with, and that's with units. So dh dt we would expect to be in meters per second. Entirely reasonable because our height is measured in meters, so its derivative would be in seconds if seconds are the time derivative variables. However, this is in liters per second, and this all over here is in 1 over meters squared. This is just a constant, but the h squared is in meters squared. And if you multiply those units out, you do not get meters per second anymore. So how will we fix that? We need to have the volume turned into meters cubed. If we had volume in meters cubed, then all of these will cancel out and we will get meters per second back. Well, if we need that, we just have to remember how to convert. We have negative 0.5 liters per second. And what I find easiest for unit conversions is writing some expression about the liters. So we want to get rid of the liters, so we need liters on the bottom. We want meters cubed, so we want that. And 1 meter cubed is the same as 1,000 liters. So that is essentially multiplying by 1. When we do that, we'll be able to cancel those units there. We end up with negative 0.0005 meters cubed per second. Liters are smaller, so we're not losing that many meters cubed per seconds. And with that, we can then sub in. We have dh dt is equal to negative 0.0005 meters cubed per second times these other constants and times the h value that we want to sub in. We want to know when this is happening when the height of the water is exactly 2, and then we go to our calculator. We end up with a negative value of approximately negative 1.59 times 10 to the negative 4 meters per second. All right, does that make any sense at all? Well, again, think back to the scale of this problem. This is a very tall tank. This is twice the height of a person, and it has quite a large cross-sectional area as well. So it's a big tank, and we're losing half of a milk jug every second. So the amount of water that we're losing per second is actually quite small. So imagine how slowly this water would be going down, and that's captured here by the very small value. We get the encouraging statement here that the derivative is negative though, which indicates that, yes indeed, the water level is dropping. The height of the water in this tank is going down because the derivative is in fact negative. So that falls out naturally as part of our calculations. So we'd say here is the water level is dropping at negative 1.59, let's make it millimeters, 10 to the minus 1 millimeters per second. So not even a millimeter per second with that slow drip that we have out of this tank. But that's exactly the rate we were asked to compute based on the rate at which the volume is changing in this problem. Now as a follow-up question, more conceptual, when the water height is above 2 meters, so we look at the scenario here, we just talked about when the water level was 2 meters exactly. Imagine what the scenario would look like, or what the consequences would be if you'd had it more full, like so. And ask yourself, is the water height changing more quickly or more slowly than the value we just found? Think about that either conceptually or mathematically, and then we'll come back. All right. Well, if we're looking at this scenario here, we're talking an h bigger than 2. One thing we can take advantage of is the relationship we just found in the last slide, which was the value for the derivative. It'll be the rate of change of the volume, 4 over pi, 1 over h squared. This is constant. We're always losing the same volume per unit time at 0.5 liters per second. Negative. This part here is also a constant. It's just 4 and pi. However, this, with a larger h, we're going to get a smaller 1 over h squared. And if we have a smaller 1 over h squared, it means that our dh dt, our derivative, is also going to be smaller. And so that would indicate that things are going to flow out of the tank at the same rate, but it's going to mean the water level is dropping more slowly because we have a smaller value for the rate of change. And again, we can also make that conceptual argument. If we're losing 0.5 of a liter, it's not going to take much out of the top part here because there's more area, versus when we're down at 2 meters, we have a smaller area, so 0.5 of a liter. It's still not going to take us down far, but it'll take us down further than when we have a bigger area. And in fact, the less water there is, the lower this water level becomes, the faster the water level is going to drop. So we can see that in this mathematical statement as well. The smaller h gets, the bigger this overall thing gets, and the bigger dh dt will get. So we can make not just quantitative statements about the rates of change like we did with a calculation and a value. We can actually make qualitative, more generic statements about when are things happening quickly and slowly, which is the real power in the application of related rates.